Hey, what's up everyone? I'm Damien. I've been looking into Cashu and building on Cashu for the last couple months, and I think that it's super fun and super exciting. There's a lot that you can build on it. So today I'm going to be sharing with you what I've learned, and we're going to be diving into the Cashu protocol. The link to these slides can be found at tinyurl.com/cashew-nuts. Alright, so a quick overview of what we're going to go over in this presentation is why Ecash, why not just keep building on Lightning, for example. We're going to touch on the history and origin of Ecash, David Chaum, who came up with the idea and started a company on it called DigiCash. Part of that is using blinded signatures, which is a key piece of Chaumian Ecash. And then we're going to talk about David Wagner, who modified Chaum's implementation to use Diffie-Hellman instead. And then we're going to go into Cashu specifically, its origins, talk about kind of the ecosystem, what's going on in it, and then actually dive into the spec. So overall, I'm hoping to help you understand the Cashu protocol, the pros and cons, and then ultimately get you building on a new and exciting protocol that has a lot of opportunity for contributions. This is a super new protocol. There's a lot of experimentation going on, and it's relatively much more simple than Bitcoin and Lightning. So I think that there's a lot of space for plebs like us to drive it forward and add our own contributions. So this is a question that has been talked about a lot recently on Twitter. Is Ecash a shitcoin? I don't think it is, but I do think it's important to understand the trade-offs, what it is, and kind of like what you're actually getting from it. So Ecash is a bearer token backed by some asset. Bearer token meaning it's literally a piece of data. And that data has no value itself, but it's backed by Bitcoin, and it's sort of a promise to give you your Bitcoin back at some point in the future. And Ecash is inherently custodial. Mints hold your Bitcoin in exchange for Ecash. You give them your Bitcoin, they give you Ecash back. And mints can turn off at any time. They can run away with your funds. Fedimint makes this a little bit harder by federating the mint, meaning the Bitcoin is locked up in a multisig, whereas the Cashu protocol is just one Lightning node. So it's much easier for a Cashu mint to disappear with your funds than a Fedimint to, but either way, they're still custodying your funds, and there's going to be trade-offs. But with these downsides come upsides. We get increased privacy. We get more flexibility in what's possible. We're not limited by the constraints that are on Bitcoin. And I think the most exciting use case of Ecash is that it's a better way to do custodial Bitcoin. So rather than just sort of giving your users a quote-unquote balance, which is just sort of like an entry in your database, you can give your users Ecash, and as an app developer, you can run a mint, and all your users' funds are held on the mint, but then they get more privacy within your app. And ideally, they should be able to go and pick a different mint. They don't have to use your mint specifically. And then another exciting use case is offline payments. It's just like cash. These are pieces of data that you can give to someone. You could put it on a USB stick. You could have them literally write it down by hand. So you don't actually need to interact with the mint, but ultimately to get settlement of that Ecash transaction, you do need to interact with the mint, but that could happen later when you come back online. Quick history lesson of where all of this came from. In 1982, David Chaum published this paper, Blind Signatures for Untraceable Payments, and this was sort of the introduction of blinded signatures and how this can create digital cash. Chaum says that this is a new electronics payment system, and with it, there's the inability of third parties to determine the payee, time, or amount of payments made by an individual. And also the mint is blinded, so the mint doesn't know any of these transactions that are going on. It's just issuing signatures. There's the ability of individuals to provide proof of payment, and this is not something that's in the Cashu protocol, but Chaum says that with it, we could stop the use of payments media reported stolen. So if your Ecash is stolen, you could report that to the mint, and then the mint could sort of invalidate that. That's not something that's in Cashu, but I guess theoretically it is possible. This graphic shows sort of how blinded signatures work. So here we have a carbon copy paper. So let's pretend that the message here is carbon paper. And you can stick that inside of an envelope, close it up, give it to the mint or anyone that can issue a signature. They sign it, but they don't actually know what this message is in here. They're just signing the outside of the envelope. And then at any point in the future, this envelope could be opened up, given back to the person that signed it, and they could verify that it is indeed their signature because it got imprinted through. They just don't know what it is that they signed. So after Chaum published this in 1982, then in 1996, David Wagner published this paper, Chaumian Ecash without RSA. And his motivation behind it was that RSA had a patent on it, and I think at the time of this paper being published, Diffie-Hellman still did have a patent, but it was soon to expire. And the problem with patents is that just like plebs like us weren't able to just go ahead and start using it. So he decided to use Diffie-Hellman. The basics of Diffie-Hellman are this. So this is without blinding. I'm not sure that this math is exactly correct, but it gets the idea across. So here, say A is Alice and B is Bob. So Alice has her private key, which is this lowercase a, and then she also has Bob's public key because it's public. And then on the other side, Bob has his private key and Alice's public key. So in order to compute a public key with elliptic curves, you multiply it by this thing called a generator point, which is shown as G here. This is just like a constant value that's used for a specific elliptic curve implementation. So in order to get uppercase B, which is the public key, you can multiply the private key by G, and you end up getting the public key. So in this case, uppercase B is equal to lowercase b times G, and then on the other side, lowercase a times G is equal to uppercase A. So with this, we can factor out G, and we end up with an equality here where lowercase a times b equals lowercase a times b. And so with this, we're able to compute a shared key. This value here is going to be used as a private key, and because of this, Alice is able to compute the same key that Bob is without knowing each other's private keys. David Wagner says in this paper that it's a lesser known fact that you can blind a Diffie-Hellman key exchange, which is what's shown here, just as you can blind an RSA signature. So we can take this and we can blind it. And again, the process of blinding is just this idea of like you stick a message in an envelope, and this envelope is blinded. It's just an envelope. You don't actually know what's inside of it. So we can use Diffie-Hellman key exchange. We can blind the secret, we can get it signed, and then we can unblind it. And then just a little note on the security of this protocol here. David Wagner says that breaking Diffie-Hellman and taking the discrete logs in this group should be hard. I think this is kind of a common theme. I'm not a cryptography expert, but a lot of these cryptographic protocols, it's like it should be hard. We don't have a real proof for it, because if we did, then maybe it would be broken, but we think that it works. And there's a lot of thought that goes into it for why it's hard to break. And he says that the security of this protocol, meaning blinded Diffie-Hellman key exchange, depends on the intractability of breaking Diffie-Hellman. So if Diffie-Hellman is secure, then blinded Diffie-Hellman is also secure. Finally, in 1998, DigiCash went bankrupt. Again, DigiCash is David Chaum's company that he was trying to build this digital cash with. And I think Callie says it best here for why they went bankrupt. He says, Bitcoin doesn't need eCash. eCash needs Bitcoin. For decades, people have been trying to build an eCash solution that catches on. Turns out you can achieve a lot more if you build on top of Bitcoin as an open monetary system that allows for permissionless innovation. Imagine building Cashu on top of fiat banks. Useless friction at every single step in the process. It's like, imagine you have like DigiCash and you want eCash from them, but how do you give them your dollars? Like, you could maybe send it in the mail, otherwise you have to make a bank transfer. It's just doesn't work. Whereas with Bitcoin, you just send them a lightning payment, drop a transaction on chain, and there's easy proof that they got paid, so then they'll issue the eCash. So Callie finishes up and says, meanwhile, we're crushing it with a bunch of contributors working on their own Cashu projects. and even receiving independent open source funding. So glad we have Bitcoin. So glad we have Bitcoiners. Amen. All right, so with these building blocks, we now have blinded digital cash, also known as eCash. And again, just to kind of reiterate what that looks like, we have Alice here on the left and Bob on the right. And Alice is, say, a eCash user, and Bob is an eCash mint. Alice can write this message, "I love JavaScript," in an envelope, give it to Bob, and Bob unknowingly is signing the fact that he loves JavaScript. And you can see here this envelope now has his signature on it, so when he gives it back to Alice, she can open up the envelope and show that Bob did in fact sign that he loves JavaScript, even though he doesn't know that he signed it. So Cashu started about 2 years ago with Kali. I'm not sure exactly when that all came around, but just looking at the repositories and stuff and like his reference implementation, it looks like about 2 years ago he started it, and he based the blinding part on blinded Diffie-Hellman. So we can see here Ruben Somson dug up David Wagner's protocol and kind of cleaned it up, and this is what we end up using in Cashu. And then there's also the token logic piece of Cashu, where Kali says that is based on Minicash, which I'm not very familiar with, but could be interesting to dig more into this. And then a brief look at like kind of what's going on in Cashu right now. Here we have Awesome Cashu, which is just a repository. You'll find a lot of software projects, like there's an Awesome Noster. I can't remember where it started, but it's basically just like a list of everything that's going on Cashu related. So here you'll find there's already a bunch of Mint implementations. We have a Python one. This Nutshell is the reference implementation maintained by Kali. And then we have a bunch of other ones here. We have wallets. These are wallets that can interact with these mints, and then a bunch of libraries. So Nutshell is also a Python library. We have a good list of TypeScript and JavaScript libraries, which we'll end up using in a future workshop for actually building a Cashu wallet. Sadly, today we're not going to actually do any coding, but I think that it should be interesting enough to kind of give you an overview of what Cashu is. And then down here we have some tools that we'll go through. We're going to talk about this numnut, and yeah. So then finally we have the spec. This is like what Cashu actually is. This is where Cashu is defined. Like if you want to know how swapping of tokens works, this is all defined in the nuts. Just like Bitcoin has BIPs, Nostr has NIPs, Cashu has nuts, notation, usage, and terminology. So we're going to dive right into those nuts here. We have nut 0, which is the basics of the protocol. It talks about the blinded Diffie-Hellman key exchange again, which is based on David Wagner's implementation. He defines some models, so these are like the common data structures that mints and wallets need to understand, and then finally the tokens. So we're going to start here with the blinded Diffie-Hellman key exchange. You can read the protocol here, but I made this Figma hopefully to try to kind of like clear it up, because it is a little bit of a confusing protocol. So here we have Cashu's blinded Diffie-Hellman key exchange. In this flow, we have Bob, who is a mint. We have Alice, who is the sending user. And then down here we have Carol, who is going to receive the token from Alice. And we're just going to follow this flow. I have these numbered here of blinding the token, or blinding the secret, signing it, and then unblinding it, and then ultimately verifying it. And just as a note, all operations here are going to occur within the SEC P256K1 curve. It's the same curve that Bitcoin uses, so it's really nice because that means that we get to benefit from all of the work and security proofs that have already been done over in Bitcoin. And what that also means is that all of the math stuff that we're going to do here is going to be performing point operations within a finite field. I'm not going to talk too much about what that actually means. Maybe we'll do a PlebDevs workshop, elliptic curve cryptography for dummies or something. But just note that like all of the stuff that looks like math that I have down here is not going to be exactly normal. It might be a little different than you're used to because it's all happening within an elliptic curve. Alright, so here I have these two screenshots from the spec. We have Bob and we have Alice. This is just showing the variables that each of them sort of knows. We have Bob, who has a private key and public keys, and then the blinded signature. And then Alice is going to have X, which is a random string. That's the secret that's being blinded. We have R, which is a blinding factor, so it just adds some extra sort of randomness to the data that Bob is signing. And then we're gonna create a blinded message, and then we'll get back this blinded signature from Bob, and we'll be able to unblind it to get a proof. And then I added here that Alice also has Bob's public keys, because she's gonna need that for unblinding. And just as a note, you'll see this is what a Mint's key set looks like. This is the public key set. So you'll notice here that there's one, these are public keys. There's one public key for every token denomination. So if you want a token worth 1, then it'll get signed with this. And if you want a token worth 4, it'll get signed with this. And these, you can create a bunch of these signatures and put them together, so you could have a signature for 1, a signature for 8, and now you have a token worth 9. Alright, so let's get into the flow here. So Alice starts by creating this random message Y, and in order to create it, she needs X, which again is it's a random secret. It's just randomly generated. It shouldn't be able to be generated again. And she performs this operation called hash to curve. Hash to curve takes an input of a random number X, and what it outputs is a public key on the Bitcoin curve. So what happens is X gets hashed, and then it gets turned into a pseudo-random public key point. So it's pseudo-random because X is random, but then it's kind of deterministically put onto the curve as a public key. So now that Alice has Y, which is a public key point, she will blind it. And that's this step here. So this B underscore is going to be the blinded message, and that's the result of adding this point Y to this other point R times G. And if you remember back with Diffie-Hellman, when we multiply by G, we get a public key. So in this case, R is going to be a private key, and R times G could be thought of as like big R, and that's the public key of private key R. And this is going to be point addition, and when you add those together, we'll end up with a blinded message. And Alice will now give this blinded message over to Bob here, and Bob is going to sign it. This is the signing step. So the blinded signature is going to be C underscore, and how he does that is he takes one of his private keys. So Alice says, I want you to sign this blinded message that's going to be a token worth 1. So he takes his private key that corresponds to 1 and multiplies it by this blinded message that Alice gave him, and can compute this C underscore. So this is sort of getting deep into the protocol. It's not super important to understand, but I think that it is interesting and kind of will help you as you're building on Cashu to understand what's actually going on under the hood. A lot of the libraries take care of all this cryptography, so you don't have to worry about it too much. You don't have to memorize it, but it's nice to know. So now that Bob has created C underscore, which again is the blinded signature, he gives that to Alice over here. And now Alice is able to do this magic to unblind it. So she unblinds C underscore to get just C, and she can do this by subtracting R times K from C underscore. So again, K is going to be the public key that corresponds to this private key over here that Bob used to sign. And she already knows R because that's what she used up here to blind it. and she's going to do elliptic curve subtraction, which is going to be the inverse of addition. This is some stuff here within the finite field. You always have to stay within the field, so you sort of like, every time you get outside of, like, say the field is 0 to 10, every time you get outside of that, you have to loop around, just like a clock. When you get to 12, you just go back to 1. And yeah, it has, the reason that elliptic curve subtraction is this way is because it has to stay positive within the finite field. So a minus b could end up being a negative number, but the end result is going to be a positive number. So with this, and I don't know how it works, but somehow magically this ends up unblinding the signature. And what Alice can now do is give this in combination with x, so x was created up here, and she can give x along with c over to Carol, and now Carol has this token, and if she ever wants to redeem that token, she can give it back to Bob, and Bob can verify that it was actually his signature. Because everything was blinded, he doesn't know that this C came from this C underscore, which is really interesting here because Alice made him sign this, and then she gave the token to Carol, but when Carol gives it back to Bob, Bob has no idea that it's the same token that Alice created in the first place. And so this is where some of the privacy comes from. So what Bob can do is take his private key, multiply it by the hash to curve of x, which again is from the token there, and it should equal C. If it's valid, then Bob will mark x as spent, so if Carol ever tries to give him the same token again, then he'll say, no, you already spent this. Alright, so that's kind of a quick overview of what the Cashu blinded Diffie-Hellman key exchange looks like. It really helps to implement it yourself if you want to understand it more, but I hope this kind of gave you a quick understanding of what's going on here. Alright, getting back to nut 0, I mentioned we have these models here. So this is sort of what it looks like. We have this blinded message. Remember, this is what Alice gave to Bob first, and this is going to have this B underscore in it, which is the blinded message itself, and that comes along with this ID, which is a key set ID, and then the amount that she wants for it. We also have the blinded signature, so this is the signature that Bob gives back to Alice, and again it has the same ID and amount. And then ultimately we have a proof, so this is what Alice is going to store as her token. So after she unblinds C underscore, she'll get C. Secret is that same X that we saw earlier, and then this ID and amount. And finally in nut 0 we have the tokens. So these tokens are going to be a list of proofs. They get encoded, so they have like this Cashu prefix, the token version, and then the actual token itself. So the tokens in JSON format look something like this. They have these proofs, which is the proof that Bob signed it, and you can see this total token is worth 10 sats because it has these two proofs in it. It also has the mint, so this is the mint that signed it, and the unit that was used. So this is a cool thing about this new Cashu v1 protocol, is that you could have any unit here that you want. In this case, it's sats. So this is the token that if you're actually sending someone Ecash, this is what you would send them, but it would end up encoded in base 64 and then put in this format here. Alright, so that's kind of the basics of the protocol. This is what an encoded token will end up looking like. And notice we're on token version 3. There's v1 and v2, which are now deprecated. Alright, now moving on to nut 1. This is the mint public key exchange. So remember, the mints have a public key set corresponding to their private keys that they have, where each of these values is for a certain token denomination. And so in order for Alice, a Ecash wallet, to interact with the mint, she needs to know the public keys. And so this is how we do that, is defined in nut 1. The wallet can request this key set by HTTP with a GET request for /v1/keys. So this is kind of fun to do here. We can use the test nut mint here that Callie has running, and see here we put /v1/keys, and what it ends up returning is this whole list of public keys. And this ID here is going to be the key set ID. And that key set ID is defined in nut 2. So this is where we show what key sets should look like and how to actually derive a key set ID. So the key set ID is going to be derived from the whole list of public keys. So the cool thing about this is that a wallet and a mint can separately compute the same ID, and you end up getting this here, which I think we see we have this key sets object, which is an array of key sets of keys. All right, so moving on to here, we're not going to go too much into these. Maybe I'll show the spec in a sec. But nut 3, 4, and 5 defines swapping, minting, and melting. So these are like the key operations of Cashu. We have swapping, which is exchanging a set of tokens for different tokens of the same value. So I have 10 sats worth of Ecash tokens. I can give those to the mint and get back 10 sats, but they'll have different secrets, and they'll be like the X that was created that got blinded will be different, and the old tokens will get marked as spent. So this is generally how like you send Ecash. Is I have my tokens, and if I want to send it to you, I will give you my tokens, but because they're just bearer tokens, pieces of data, I can keep a copy of it for myself, and there's nothing preventing me from double spending. So what you have to do to ensure that you actually received that Ecash is you swap it with the mint. So the tokens that I gave you, you'll swap with the mint. Those will get marked as spent. So now if I kept a copy, they'll be invalid, and you'll get a new set of tokens worth 10 sats. And then there's minting, which is how you actually create new tokens. So in this, we give the mint blinded messages to sign along with a proof of payment. So the proof of payment is probably going to be like the mint gives you an invoice and you give them the pre-image back, or they just like verify that the invoice was actually paid, because they're not going to give you money unless you give them money. And then the mint will end up giving you these blinded signatures, and the wallet can unblind them to get tokens. So this is how we give the mint our Bitcoin and get back Ecash. And then if we ever want our Bitcoin back, we melt our tokens, which is where the wallet provides the mint with its proofs. Again, these are the array of these signatures and secrets, along with the key set ID, which was the key set ID used to sign those tokens, and then an invoice. So we give the mint proof that the mint actually signed it, and then we say, here's an invoice I want you to pay. If all these proofs are valid, then the mint will pay the invoice for you. So you could have your Lightning wallet generate an invoice, send it to the mint along with your tokens, and they will pay it for you, effectively giving you your Bitcoin back. Or you can use it to pay someone else Bitcoin. And I guess I'll just show, because this can be a little bit confusing. This is going to be more in a workshop on actually building a Cashu wallet, but it could be nice for you to see here. So there's sort of a flow that is a little bit unintuitive at first. So this is nut 4, which is for minting tokens. What we do here is we send a post request to the mint for a mint quote. So a mint quote is basically like telling the mint, I'm ready, I want to mint some tokens. And you'll notice here that the spec has this method here. It only talks about bolt 11, but in theory you could add any method here that you want. So when you hit this bolt 11 endpoint, that's saying that you're going to pay a bolt 11 invoice. So Alice, the wallet, will send to the mint a post mint quote bolt 11 request, which has an amount and a unit. So she could say, I want to mint 10 sats, give me an invoice. So when Bob gets that request, he responds with this object here, which has a quote, which is just an identifier for this specific request. This is the actual request. In the case of a bolt 11, then this will be an invoice to be paid. And so now Alice has this invoice associated with this quote. And then, oh, here we see an actual example of it, where Bob responds with this random string and the actual invoice, but it's not paid right now. So then when Alice actually wants to mint the tokens, she hits this mint bolt 11 endpoint and gives Bob back that quote ID along with the blinded messages to sign. So when Bob receives this mint request, he will look up this quote and verify that the invoice was paid. And if so, he'll take these blinded messages, sign them, and return to Alice these signatures. So again, he took Alice's Bitcoin and gave her Ecash in return. All right. And then finally, in the required nuts, we have nut 6, which is the mint's information and settings. So here is kind of like where you can figure out what a mint is actually capable of. If we go back here, we can hit the v1/info endpoint. Oh, I can do my cool pretty print here. And see, I'm hitting the test nut here, and we see that it's a Cashu mint, version is running on Nutshell, and then we can see like sort of what it's capable of. It has different methods for nut 4 and 5, which is minting and melting. So we can see we can mint and melt both USD and sats, and then here he's signaling support for all of the other nuts. And all these other nuts that he's signaling support for are optional nuts. And these are things that are cool to have, but not necessary for the base functionality of Cashu to work. All right, so that was a lot. Let's look at this Cashu simulator, which I hope will kind of tie this all together for you. And then we're actually going to end up running Nutshell and sending some Ecash around. So that should be pretty cool. So if you go to numnut.gandalf.com, again, this can be found also on the awesome Cashu GitHub repo. If you go here and select this single nut, we have here a Cashu protocol step by step. So the first step here as a wallet is to generate a super secret, and I'm going to spell it with 2 T's so that no one knows. And we'll choose this secret. So now here you can see in the local data, hopefully you can see if it's big enough. In the local data on the wallet side, we have a secret. Now we're going to take that secret and create a blinded message, which doesn't work. Let's refresh. I'll just generate a secret this time. And then create a blinded message. Okay, it worked that time. So now we can see we had X, and then we took this blinding factor R, created this secret on the curve, and then we are ultimately able to create this blinded message. So this is all still in the wallet. We can now send this over to the mint. So now in the mint's local data, it has its public key along with this blinded message generated by the wallet. So now the mint will sign it, and the mint has this signature here, and we can send this signature back to the wallet. The wallet now has this blinded signature, but we can unblind it, and we get this. So now this is effectively a token. This is Ecash. This C combined with X. And now we can redeem it at the mint. The mint now received X and C. The mint can verify it and considered valid. And now the mint adds that secret to its list of spent secrets. We can also check out, let's see, how do we get there? If we go back here, And check this out. I'm just going to run through this really quick. But now we have 3 wallets and 1 mint. We have wallet 0 can mint tokens. Down here, the mint can sign it. And now this wallet has Ecash. And again, because they're bare tokens, when I send this over here, now wallet 1 has Ecash, but they're the same. Notice this is the same X, 3DCF, 3DCF, and we can even send this again. So now all of these wallets have the same tokens. But now what can happen is, say, this wallet will redeem it, and the mint down here adds it to its list of spent secrets. And these wallets still have this Ecash, but if I try and redeem here, it just won't work. This wallet has redeemed 1 token, but this one won't work because it's already been redeemed. It's spent. Alright, so this is fun to mess around with. Hopefully it kind of gives you a better idea. Again, we can see like the blinded messages here. This wallet created it. These ones have the tokens, but they don't have the blinded messages. Alright, so now let's actually build and run Nutshell. Nutshell is the reference implementation for Cashu, and it'll allow us to have a Cashu wallet and actually start using Cashu. So one thing to note is that Nutshell, Callie is a speedy coder, and he's constantly adding new things. It's probably a ton of steps ahead of what everyone else is at, of where the actual current state of the spec is at. I've had it a couple times where I'm looking into Nutshell, trying to figure out how something works, and I'm like, wait, this isn't in the spec. But Callie is just kind of experimenting with things, and don't take everything in there too seriously. There's also a lot in there, so it can be a little overwhelming if you're actually trying to look at his code. So we're gonna build and run Cashu. You can find the instructions here in the README, and just a note, we're gonna be using poetry, and here are the instructions. And I always just, like, if I see a code block like this, I just copy paste the whole thing. But you'll notice that Callie has some kind of instructions here, like install this and then follow the instructions. So we kind of have to do these one at a time. And also this is going to be on Ubuntu, but luckily here we can ask ChatGPT. So I can say, like, okay, these instructions are Ubuntu, but that's okay because I have ChatGPT. So I'm running on Linux, so I can just run these commands. But if you're running on Mac or Windows, just ask your friend here and say, hey, I'm using Mac OS. Can you help me run these commands that are meant for Linux? And we'll just copy those in, and then ChatGPT should spit out something that works. It may not be perfect, but it should kind of like give you the most notable difference here is that we're using brew to install versus in the docs here we're using apt. These are just different package managers. But if you're not on Ubuntu and if these instructions don't work, ChatGPT is your friend. All right, so I'm gonna open up a terminal. I don't know what I just did there. I'm going to open up a terminal here. And stick this on the side here. Alright, so I will just paste this in. Mostly just copy and pasting. I've already done this, so it should go fast. I've already installed Python. I'm not going to do that again. Let's see what happens if I run. I've already done all this, so might be a little different for you. You'll notice here, this is where some instructions are needed. You'll need to add this into your bash rc file. So we can see here I have this file that is on every Ubuntu machine. I don't know how it is on Mac, but you may need to, again, ask ChatGPT for this. But I have this here, and at the end I added this from those instructions. So what I should now be able to do, he says here, restart your shell or source the RC file. So if you had just added files here, they won't take effect in this terminal. until you say source./.bashrc, or you can restart the terminal and load it up again, and those changes will take effect. I have already installed this. I have already installed Poetry, but those, you should be able to copy and paste those and get those going. So now what we're going to do is, that's wrong. We're going to clone the repository, and we're going to go into it. We're going to check out the latest tag. So you can find that in the releases of the repository here. So we're on 0.15.3. So if we go in here, cd into Cashu, another thing that you can do is git tag -n, and this will show you all of the git tags. These RCs are release candidates, so we shouldn't use those unless we're developing on this. But we're gonna just check out this tag here, which is the latest release. So we'll do git checkout that tag, and now we are on the latest stable release. Now we're just going to start up our virtual Python environment. Now we're in there, and let's do Poetry install. So this is just gonna install all of the dependencies that are needed for Cashu. So now we should be pretty good. What we need to do now is enter our Poetry shell, and I'm just following these instructions here. Now we need to set up our configuration. So if we open this up in our code editor, we can see we have this .env.example. We're just gonna move this to .env, and that effectively just renames it. And you should be able to pretty much leave everything here. You can mess around with whatever you want, but what I'm gonna do is set this mint URL. So you could run a mint locally if you want, or what we can do is there's this handy website, bitcoinmints.com, which will show you a list of a bunch of mints. These are all published on Nostr, and they all have reviews. So like Minibits is by far the most popular one, and you can go and look at who you follow on Nostr that recommended this mint. So we can do that, or if we look in here somewhere, he shows this is the test mint. So this will not be real Satoshis, but you can test it out with that as well. I'm gonna go reckless mode and just copy Minibits. Again, this is custodial, so you're giving your Bitcoin to someone else, and they're giving you Ecash, so don't put too much money on here. But I just copied this mint URL, and I'm gonna put that in here. So what we have here is now Cashu's nutshell, and we're gonna have a wallet that's gonna use this mint. So I'm just gonna restart my Poetry shell. I'm not sure if it takes effect with that environment. So we start up Poetry shell, and if we go back to the docs here, we'll see a bunch of commands we can run. So we could try Cashu info. Let's actually mint some tokens. So with Cashu invoice, I'm gonna just say 50. We're gonna be requesting a, let's see. Okay, I already installed this, so it's actually using my environment, or my like data directory from before. So that's okay. It's just saying I have 2 mints here, and I'm gonna pick mint 1. And I chose to run on Tor, which gives you more privacy because, again, this like the blinding of the tokens, that's private, but the actual interactions with the mint are happening over HTTP, so you're exposing your IP address. So by using Tor here, you'll probably need to have Tor installed and like have a Tor something or other running. But if you don't, you can just go in your environment file here and set this to false. So what it did here is it gave me this invoice. I will copy it, and I'm just going to use Albi to pay it. I just requested from the mint. I said I want to mint some tokens, and it's like, okay, here's an invoice for you to pay. If you pay it, I'll give you tokens. And you can see here it checked it and says invoice is paid. So if I again do Cashu info, we will see, let's see, I can do Cashu balance. Oh, wait, now I have 2 mints, and this pending is from before, so we'll actually see that in a sec. So I have 50 sats, but 25 of them are pending, and this has to do with the swapping of tokens. I created some tokens, so I did this. I said Cashu send 25, and again it's asking me which mint I want to use. I'm going to pick mint 1, and it will create some tokens for me, hopefully. So here is the token. And now what I can do is go into, if we look at Awesome Cashu, there's a whole list of wallets here. I'm gonna choose cashu.me because I already have that set up. So now what I can do, I just remember copied this token here, and I can click receive Ecash, paste this in here, and I should get 50 sats now. But if I go back here and say Cashu balance again, we'll see now I have 50 pending sats. So let's see. I'm actually not sure how to check these. It doesn't show up right here in the docs. Seems like it should check for me. Let's see what happens if we try to send again. Because these tokens that are in this pending state are actually already spent because I redeemed them in my other wallet. I'm going to pick this one. Exception, balance too low. Well, it says my balance is 25, but 50 are pending. I'm not sure, I haven't used Nutshell much. That could be a challenge for the reader, is figure out how to get your tokens out of a pending state. But if we do this again, well, okay, so these ones, I guess I did have still balance. So I'm gonna receive this, and I just wanna try and show you what happens if I receive 25 sats. And now if I try again, I shouldn't have any more valid tokens. So let's see what happens. Exception, balance too low. So yeah, these are still in the pending state. I still have 0 sats in my balance. That's why it's giving me this. But is there like a Cashu help? Cashu help. Boom. Let's see, we've got swap, balance, send, receive, burn, spent tokens. Cashu burn. This is just some experimentation here. I'm gonna finish this off in just a minute. We're about at an hour. I don't know. Anyways, I hope you can see here, this is what it actually looks like to use Cashu. Yeah, so see, I just did Cashu burn -- all, and now I don't have a balance in that mint anymore. Alrighty. And finally, some additional resources for you to continue digging into Cashu. We have this cool Cashu decoder here where you can paste in tokens. It'll decode them for you if you want to see what they look like. Cashu.space is the docs. You can see the whole Cashu BTC GitHub repository. Again, awesome. Cashu is a great place to kind of like see what other people are doing, get a feel for how to start building wallets. And then of course, PlebDevs, check out the PlebDevs website and join the PlebDevs Discord. And finally, again, I just want to say I'm going to do a workshop on actually building a Cashu wallet. This was just sort of an introductory, hopefully get your feet wet, understand how Cashu works and what the protocol is doing. But looking forward to creating this Cashu wallet workshop, and I hope I'll see you there. All right. Thanks, everyone.